You deploy an app to Kubernetes. It gets an IP address, and somehow other pods can reach it. Then a pod restarts, gets a completely new IP, and everything still works. That is not luck. It is a carefully designed networking model with clear rules. In this video, we unpack that model layer by layer, from a single pod all the way to production traffic entering your cluster. Here is the roadmap. We start with the 4 networking rules Kubernetes demands from every cluster. Then we look inside a single pod, move up to pod traffic, and introduce services and DNS that give us stable names. After that, we cover the different service types, Ingress for HTTP routing, the CNI plugins that make it all real, and network policies that lock it down. By the end, the whole picture will click. Kubernetes does not implement networking itself. Instead, it defines a contract that any network solution must satisfy. There are 4 core requirements. Every pod gets its own unique IP address. Pods can talk to all other pods across nodes without network address translation. Agents on a node, like the kubelet, can reach pods on that node, and the IP a pod sees for itself is the same IP others use to reach it. This flat model is the foundation everything else builds on. Why insist on a flat network with no NAT between pods? Because it makes the mental model simple and portable. Applications can treat every pod like a machine on a big shared network, exactly the way they would on a traditional data center LAN. No port juggling, no rewriting source addresses, no surprises when a connection crosses a node boundary. That simplicity is why this contract has stayed stable while the implementations underneath have evolved. Now zoom into a single pod. A pod is not one container in isolation. It is a group of containers that share the same network namespace. That means they all share one IP address and one set of ports. Containers inside a pod talk to each other over localhost, just like 2 processes on the same machine. This is why a sidecar container can proxy traffic for your app without any special routing. The shared namespace is created by a hidden helper called the pause container. It starts first, claims the network namespace, and holds it open. Your actual containers then join that same namespace. Because the pause container just sits there doing nothing, a network identity survives even if your app container crashes and restarts. That stability is why every container in the pod keeps the same IP for the pod's whole lifetime. So pods have IPs, but pod IPs are ephemeral. Every time a pod is rescheduled or scaled, it can get a brand new address. If your front-end hard-coded a back-end pod's IP, it would break constantly. This is the core problem services exist to solve. A service gives a stable virtual IP and name that front a changing set of pods, so callers never need to know or care about individual pod addresses. A service selects pods using labels. Here we define a service named backend that targets any pod labeled app equals backend. It listens on port 80 and forwards to the pod's port 8080. The cluster IP field, when left to default, gives this service a stable virtual IP that lives for the whole life of the service. Kubernetes keeps a live list of matching pod IPs behind that virtual address. The live list of pod IPs behind a service is tracked in objects called endpoints, or in modern clusters, endpoint slices. As pods come and go and pass their health checks, the control plane updates these lists automatically. This is the piece that makes the stable virtual IP actually point at healthy, running pods. When a pod dies, it drops off the list within moments, and traffic stops flowing to it. How does traffic to that virtual IP actually reach a real pod? On each node, a component called kube-proxy programs the operating system to intercept packets aimed at service IPs and redirect them to a chosen backend pod. Classic clusters use iptables rules, and higher-scale clusters use IPVS for faster load balancing. Newer setups may skip kube-proxy entirely and let the CNI handle it. Either way, The virtual IP is not a real machine. It is a set of rules on every node. Quick checkpoint. So far we know pods get unique IPs on a flat network. Containers in a pod share one namespace over localhost, and services give a stable virtual IP that load balances across a live set of pods using kube-proxy rules. That solves stability, but there is still a usability gap. Nobody wants to remember virtual IP addresses. That is where cluster DNS comes in. Every Kubernetes cluster runs an internal DNS server, usually core DNS. When you create a service, core DNS automatically creates a DNS record for it, so your front end can simply connect to the hostname backend, and DNS resolves it to the service's virtual IP. Across namespaces, you use the longer form, servicename.namespace.svc.cluster.local. This is why applications reference each other by clean names that never change even as pods churn underneath. Not every service works the same way. The default type, cluster IP, is reachable only from inside the cluster. It is perfect for internal APIs and databases that should never be exposed to the outside world. Its virtual IP has no meaning beyond the cluster boundary. Most services in a real deployment are cluster IP, quietly wiring your microservices together on the private network. When you do need outside access, one option is node port. It opens the same high-numbered port on every node in the cluster, typically in the range 30,000 to 32,767. Any traffic hitting that port on any node gets forwarded to the service. Node port is simple and works anywhere, but exposing raw node ports is clumsy for production. It is usually a building block rather than a final answer. The third type is load balancer. On a cloud provider, creating a load balancer service asks the platform to provision a real external load balancer, like an AWS or Google Cloud load balancer with a public IP. That load balancer forwards traffic into your node ports, which forward to pods. It is clean and production ready, but there is a catch. You get one external load balancer per service, and cloud load balancers cost money. 10 services means 10 load balancers. That cost and sprawl problem is exactly what Ingress solves. Instead of one load balancer per service, you run a single Ingress controller behind one load balancer, and it routes incoming HTTP and HTTPS traffic to many services based on the hostname and URL path. It is a smart Layer 7 reverse proxy living inside your cluster. One entry point, many destinations, driven by simple routing rules you declare as objects. Here is what an Ingress rule looks like. This one says any request to shop.example.com with a path starting at / goes to the shop service on port 80. You can add many rules from many hosts and paths in a single Ingress object. The Ingress controller, often Nginx or a cloud-native controller, watches these objects and reconfigures itself instantly. This is also where you attach TLS certificates to serve HTTPS. A modern successor to Ingress is the Gateway API. It splits responsibilities so platform teams define the gateway and its listeners, while application teams define routes that attach to it. It handles more than HTTP, supports advanced traffic splitting, and is more expressive for large organizations. Ingress is still everywhere and perfectly fine for most cases, but knowing the Gateway API exists tells you where Kubernetes networking is heading. Checkpoint again. We now have a full path for traffic. Inside the cluster, pods find each other through services and DNS names. From outside, traffic enters through a cloud load balancer into an Ingress controller, which routes by host and path to the right service, which load balances to healthy pods. But one big question remains. Who actually assigns pod IPs and wires the flat network together across nodes? The answer is the CNI, the Container Network Interface. Kubernetes deliberately does not build the pod network itself. Instead, it calls a plugin whenever a pod starts, and that plugin assigns the IP and sets up the routes so the pod can reach everything else. Popular CNI plugins include Calico, Cilium, and Flannel. Choosing a CNI is one of the most important decisions when you build a cluster, because it determines performance, features, and how policies work. CNI plugins connect nodes in different ways. Some use an overlay network, wrapping pod packets inside another packet using encapsulation like VXLAN, so pods can talk across nodes even when the underlying network knows nothing about pod IPs. Others use native routing, where the real network is taught the pod routes directly, avoiding encapsulation overhead. And some, like Cilium, use eBPF in the Linux kernel for high-performance routing and observability. Each approach trades simplicity against speed and features. Remember the flat network rule that every pod can reach every other pod. By default, that means a compromised pod can talk to anything, including your database. That is a security risk. Network policies fix this. A network policy is a firewall rule expressed as a Kubernetes object that says which pods are allowed to talk to which pods on which ports. But there is a crucial detail. Network policies only work if your CNI plugin enforces them. Here is a network policy that protects a database. It selects pods labeled app equals database and allows incoming traffic only from pods labeled app equals backend on port 5432. Everything else is denied. The important insight is that the moment you apply any policy to a pod, that pod switches from allow all to deny all except what you list. Network policies are additive whitelists, which is exactly how you want security to behave. Let us trace one full request to make it concrete. A user hits shop.example.com. DNS points that name at the cloud load balancer's public IP. The load balancer forwards into the Ingress controller. The controller matches the host and path rule and picks the shop service. The service's virtual IP, via kube-proxy rules, load balances to a healthy pod chosen from its live endpoint list. The CNI ensures that pod is reachable, and a network policy confirms the traffic is allowed. Every layer we covered plays a part. Let us lock in what you now understand. First, Kubernetes networking is a contract of 4 rules, built on a flat network where every pod gets its own IP and no NAT sits between pods. Second, services and cluster DNS turn ephemeral pod IPs into stable names, load balanced by kube-proxy across live endpoints. Third, cluster IP, node port, and load balancer expose traffic at different scopes, and Ingress consolidates external HTTP routing behind a single entry point. Fourth, CNI plugins actually build the network, and network policies fence it off. You can now reason about traffic at every layer, from a single pod to production. If this made Kubernetes networking finally click for you, subscribe to Nodebound. We break down one cloud and DevOps concept at a time in plain language, so the systems you run every day stop feeling like magic and start feeling like something you truly understand.